Tēnā koutou, ko Brian Elaine toko ingoa, Program Manager here at Te Ao Rangaho. Welcome to our 11th Climate Conversation, which is our series that we put on around monthly to support our engineering climate action. Today we'll be hearing from Transition Engineer Nathan Surendran, who will give a high-level view of the global drivers of change. But before he kicks off, I'd like to introduce our MC for this conversation, Bridget Doran. Bridget is a chartered engineer at MR Cagney with significant experience in transport policy, design, community engagement and participation planning. She generously gives a significant amount of her time, voluntary time, to Te Ao Rangaho, and currently as part of that sits on our climate action steering group. So welcome to everyone, and I will hand over to you, Bridget.
Kia ora, Bryony, kia ora koutou, ko irihai toku iwi no kirikiri aho, ko Doran toku whānau, ko Bridget toku ingoa. Thanks Engineering New Zealand for hosting this webinar series of climate conversations. It's just a delight to be here and to have Nathan come along as well. So today we are going to discuss energy futures and a net energy lens perspective for Engineering New Zealand. And I don't have on hand a bio introduction for you, Nathan, so I might get you to do that yourself. I'll just explain how this webinar is going to work. Nathan is going to present for 25 minutes or so, and then we're going to open it up to questions and discussion. So you'll see in the bottom of your screens the Q&A, or at the bottom of my screen anyway, the Q&A box. Feel free to type any questions or comments in there as Nathan is presenting, and then when he's finished I will facilitate some answering and discussion of those questions. So without further ado, I'll hand over to you, Nathan, and thanks very much.
Thank you, Bridget. Kia ora koutou, nā Nathan Surendran aho. I'm a building services engineer by background and training, was chartered in 2009 through the Chartered Institute of Building Services Engineers in the UK. I've been in New Zealand since 2010. I've professional energy expertise, which includes building physics and the science of the energy flows through buildings, be that heat flows, electrical flows, etc. But I've broadened my scope over the last decade or so to include a more informed perspective on global energy supply systems and trends, because I found when I was made redundant in about 2009, shortly after I was chartered, that I had a bit of time to think, and I started reading. And I don't know about you guys, but I find that reading is something of a dangerous thing to do. So I read Limits to Growth, read a load of stuff on biophysical economics and biophysical perspectives on the global energy system, and as a result have made some different choices in my professional career, which I'll talk a little bit about in the discussion if anyone's interested. Anyway, I'm hands-on. I've built my own off-grid passive solar low energy house in Clifton in Invercargill over the last few years, and I'm engaged and committed to educating society about energy, and specifically this net energy perspective, which I believe is significantly underappreciated, and also a significant perspective which we must be incorporating into our climate change conversations and engineering practice. So this presentation, my basic contention is that engineering as a profession needs to shift our perspective to overcome our blind spots, particularly with respect. So in that context, we need to understand the broad perspective on what's being called now the poly crisis, or sometimes meta crisis, how vulnerable we are in New Zealand, how fundamental oil is to our industrial economy, how much work our net energy slaves do for us, our energy slaves, sorry, and how quickly the net energy from oil supply is changing globally. I'll talk a little bit about economic analysis that's fundamentally blind to this perspective, and because our strategic futures are being based on this energy blind economics, what are the implications for well, transportation I've got there, sorry, that's more generally engineering in Aotearoa. So, as I say, the climate conversations can't ignore the poly crisis. Can I just check, are you seeing my slides roll over? Yeah, okay, good. This is a slide which you may have seen. It's a broad list of the different things which we might have to, which we do have to consider in the context of climate change. And the contention of this image is basically that we have this filter on, this kind of blinkers almost towards carbon emissions, and that seems to be a general failing of our education system and of the conversation that we're having as a society. I'm going to talk today specifically about resource scarcity as one of the other factors in this poly crisis around the sustainability transition. And as I say, my contention is we really need to take a closer look at this specific issue. So taking a long view on the carbon pulse, you may have heard of Hubbert's curve, the idea that fossil fuel supply being finite on this one planet that we have. Over a long view, say plus or minus 5,000 years, will look something like this. We reach a peak in rate of supply and we come back down the other side. Now, this is a chart from the 1950s where it was thought that nuclear energy could be scaled up to provide a steady high level of energy resource to us that the fossil fuels wouldn't be able to sustain. Unfortunately, that hasn't happened. And so we're stuck with where we are on fossil fuels, and where we actually are is somewhere around the peak of this rate of supply. And that's according to, for example, the International Energy Agency and many industry commentators. So the main facts around which this presentation is formed, underlying all economic activity is energy expenditure. Nothing we do that creates GDP activity doesn't use energy. And fossil fuel energy, particularly oil and specifically diesel, is the lifeblood of industrial society. It's a non-renewable, depleting resource, and its extraction and use is subject to diminishing returns. You'll notice on most of my slides I have some links down the bottom right. There's a fair bit of reading and research behind this presentation, and feel free to follow the links and dig into the detail as you are interested in the different parts of this. Now I'm going to say our situation isn't very different to Australia because I haven't created a chart like this for New Zealand. This was created by these guys at crudeoilpeak.info, and basically what it's showing is that Australian diesel imports to February 2023 on a 12-month moving average are primarily sourced from places around the South China Sea, so South Korea, Japan, Taiwan, Malaysia, and Singapore. We know that in New Zealand we're not much different. I think we have a heavier reliance on Singapore specifically, but there are some imports from other sources as well. And New Zealand is most definitely more vulnerable to disruption in supply post Marsden Point. This is a quote from the Northern Australian Strategic Policy Centre's Dr. John Coyne, where he said they're very naive and they're going into a very dated view of globalization. They certainly haven't learnt the lessons from COVID-19 around secure supply chains and national resilience. When we think about our reliance on 100% of our oil supply from imported refined products. So the refineries that we reliant on are primarily the Singaporean refineries. There's lots of stuff that a barrel of oil can do for us. These are some of the things that it can do, and I've put circles around the ones that specifically relate to transportation and mobility. But you can also generate 70 kilowatt hours of electricity at a power plant, but from the residual fuels, liquefied gases such as propane to fill some cylinders, wax crayons, charcoal briquettes, and a variety of other things. What I'd really like to focus on with you as engineering professionals is oil's outsized contribution to our lives. So an average human working all day generates around 6 kilowatt hours of useful energy output. 1 barrel of oil contains around 17 kilowatt hours of fossilized and geologically processed solar energy. Therefore, 1 barrel of oil contains around 10.5 years of human labor. Now, obviously, there's conversion losses involved in that, so we actually get around 4.5 years of useful energy as work done at the point of use from that barrel of oil, and that barrel of oil currently costs, let's say, around $100 US. So if we were to pay for that energy output as human labor, each barrel of oil, with an average salary of 50,000 New Zealand dollars, say, would be worth 4.5 times 50,000, 225,000 New Zealand dollars. We currently use around 100 million barrels of oil per day globally, and New Zealand uses around 130,000 barrels of oil per day. That is, the oil energy used in New Zealand, it does for us in one day, 4.5 years per barrel of work times 130,000 barrels is 585,000 years of human labor equivalent work per day. This is a vast energy subsidy to our society, and it's something that's invisible to us. We're just accustomed to it, but it is a reality which we must consider in the context of climate conversations. Energy profit is the next thing to consider. So having understood the outsized contribution of oil to our economic system, we now have to think about how that contribution is changing over time. And energy profit net of the cost of production, which can be likened to Darwinian fitness as an analogy, is the idea that if, for example, a cheetah expends more energy chasing prey than it gets from eating that prey, it will eventually starve. Similarly with our oil system, if we are expending more energy on the extraction, transportation, processing, transportation, and end use than we get from the oil, then eventually the industrial economy starves, in the sense it will be starved of energy. The rate of change of net energy is exponential. That is to say, it's going up in a percentage rate, and percentage rates compounded over time lead to exponential curves, as we all know. So this chart is a relatively simplistic chart. I've steered away from more complicated analysis because I think we need to come back to the simple facts of the matter to really be able to talk about this. So we have on this chart time on the x-axis, energy delivery rate on the y-axis. There's the gross energy delivery rate, which is the thing that you usually see in oil supply or energy supply analysis. And what's termed there the energy subsidy is the amount of energy that is required to extract and process and transport the resource. So the net energy delivery rate is the energy delivery rate net of the cost of production and transportation and refining and so on. And ultimately, as the net energy rate increases, as the energy subsidy increases, the net energy that we get from that resource decreases. And ultimately, there's a resource cutoff point where, even though we talk about the total amount of energy that we have available in billions of barrels of proven oil reserves and so on, some of that resource is unrecoverable. That is to say that we would spend more energy getting it out of the ground and refining it than it would give us back. Therefore, it wouldn't be profitable from an economic point of view, and therefore it will stay in the ground. When will this happen? Well, this is a recent chart of actual production of oil. So we see the rate of production, which is the blue curve, cumulatively increases, and round about where we are now in 2023, we've produced about 1,380 gigabarrels of oil. Now we have a significant amount cumulatively in discoveries, but you'll see that as that discovery rate is declining, and you can see here discoveries minus production, we've got this drawdown on our total amount of resource still available to us. Ultimately, where those lines cross, that's a point where all of the oil will have been produced that can be produced. So, how are we doing with our energy transition? The reality of our current energy transition is reasonably well known, and we can see here that wind and solar, the renewable energy machinery that we're building to power our civilization going forward as we try to get away from this use of the fossil resources is happening. It's picking up pace. However, the scale of the challenge is the key thing to take away from this slide, and we have this outsized contribution still from those resources. And as I said, specifically diesel within the oil supply part of that chart is something that is really changing quickly in terms of the total global supply rate. It's worth noting as well that as we've gone from the conventional production up until, say, the mid to late 90s, we have moved away from the heavier crude oil, which is the primary source of diesel, to things like fracked oil, which has been the energy growth, the growth in oil supply over the last 10, 15 years at least. And that is a much lighter type of oil. It's sometimes known as condensate. And you can produce some of the heavier fractions from that, but the total quantity of diesel that is coming out of the mix of our global energy supply is plateaued and is kind of showing signs of looking like it will decline. So that's something to talk about in more detail if anybody wants to at a later point. So then when we think about some of the projections that we see from, for example, the economic modeling that's done, things like the Business Energy Council's models, the Times model for New Zealand, we do see some projections which show a growth in energy consumption and a growth in oil consumption. We've seen a global growth in total energy of around 3.5% per annum historically since we started using oil in the 1920s. Because of the nature of compounded growth rates, in the last 20 years, we've consumed the same amount as the previous 80 years, growing at that rate or around that rate. And the amount of oil we consume in the next 20 years at the same growth rate is the rest of the proven resource, which again, kind of relates back to that earlier slide that I had showing there is a point at which the total amount that we produce cumulatively exceeds the total cumulative discoveries. But my contention is, going back a couple of slides before that, that actually well before that point, it's likely we'll reach the point where the net energy, net of the cost of production, tends to zero. So this wouldn't be such a problem. And as engineers, we really aren't taught enough, in my view, about the economic angle. if mainstream economics wasn't so energy blind. This is an observation from Steve Keen, who's a economist who's been looking at this issue of energy and its contribution to production. And he made the observation that labor without energy is a corpse and capital without energy is a sculpture, which is just a simple way of saying that energy is the industrial economy, that we don't do anything in the modern economy that requires that produces GDP without requiring energy inputs, and significant ones at that. There we go. Now, why is this such an issue? Well, we've seen a lot of price volatility over the last decade or two in terms of our oil supply. You know, if we took this trend back historically, you know, there's a relatively smooth, with certain exceptions, the 1970s and so on, but fairly steady price of oil around the sort of $20, $30 a barrel. And since the turn of the century, that oil price has spiked and crashed and kind of come back up and stayed there for a few years and then crashed again. And then we're back up and down, up and down. The point here again is that prices up in this high range, you know, say above $100 a barrel, and even certainly down here above 60, 80, 70, $60 a barrel, appear to be too high for some consumers because they are prices that are reached, and then that increase in energy prices has a recessionary effect, and that causes a slowdown in economic activity and causes a drop in demand, which then causes a drop in the prices. Down at the bottom end of this range, these prices are way too low for producers. So yes, historically we have the major fields which are still producing somewhere way down here at maybe $20 to $40 a barrel. But when we're looking at the marginal cost of new production, it's now on average much closer to $100 a barrel than to 40. That is to say that new supply that's brought into the market from an investment point of view requires oil prices to be seen to be sustained above the cost of producing them. And if the cost of producing them is something close to $100 a barrel and we can't see prices staying above that, then we see the effect that we have in the marketplace whereby the energy supplies aren't developed. And so we're starting to see a curtailment or a reduction in the total rate of production because of that effect as well. So, as I say, mainstream economics is failing us. To be useful, it must incorporate this biophysical reality that I'm pointing to here, and it currently hasn't. So specifically, it's fundamentally energy blind. Energy's contribution to economic activity is hugely underestimated. And there's a bunch of erroneous underlying assumptions in cost-benefit analysis models, which I feel as engineers were well placed if we understand this energy story to interrogate and challenge some of these assumptions. There's a variety of economic dogmas which we are often subjected to, and these are some of the different things that people will just kind of trot out, whether they're economists or not, when we're talking about this sort of thing, and no doubt some of you are thinking some of these things at the moment. For example, you know, models show that economic models have shown that climate change effects on economic output are minimal. The invisible hand of the market will provide. Substitutability of resources means that we can expect new energy sources to be available to replace fossil fuels, e.g. the common discussion around hydrogen, which again, we can get into in the discussion hopefully a little bit. Decoupling economic activity from energy use and emissions intensity is possible. But again, these are the sorts of things that people say. And what I've done here is I've provided links to articles which have further references that hopefully help you to understand the rebuttals to some of these thoughts, because it appears not to be the case. And again, technological progress will overcome biophysical limitations and costs will continue to reduce. So our renewable future, build out of renewables at the scale that supports business as usual is implausible. So we've talked a bit about how the economy is already maxed out in energy supply terms. Where does the energy, the diesel specifically, that needs to be invested to build the renewables come from? This renewable energy machinery, which if we're going to replace fossil fuels with it, it's probably about an order of magnitude larger because of the lower quality energy resource, the wind and solar that it's extracting that energy from. The build out requires resources at a global scale that simply aren't there. That's material resources in particular. And we can talk a little bit about that in the discussion as well. I've got some further slides in the notes which talk to that point. The renewable energy systems proposed have a design life of around 25 to 30 years. So even if we can do this transition once, could we do it twice? And from an ethical perspective, from an intergenerational equity perspective, which is often the conversation that I recognize that people with a focus on the technical aspects of the transition tend to steer clear of, but just reminding you that you sign every year when you're an Engineering New Zealand member, the Code of Ethics, that leaving some resources in the ground so that future generations have the agency to make their own decisions on its use is the ethical thing to do. So transition to 100% renewable energy, sure. You know, maintain current levels of growth and consumption. No, I'm afraid I don't believe that's going to happen. Where does this leave us? When I first came across some of this information, I really had a reaction to it that was more emotional than rational, and it's very difficult. I want to acknowledge it is very difficult to think about these things and to be able to process them in a way that allows you to then move forward and action things professionally that will actually address some of these issues. And happy to talk a little bit about that if we want to. I'm going to finish with a little exercise, which hopefully will just get you out of your sort of rational brain a bit and back into your body, which is start by crossing your arms. Right, stand up a little bit, so you cross your arms like that, like you normally do, and then what I want you to do is to cross your arms the other way. So undo your arms and cross them the other way. What you'll notice about that is that you have to think about it. It takes a little bit of time, kind of feels uncomfortable a bit at first. And it's something which actually, if you practice it, you do it repeatedly, then actually it becomes easier. And that's just a little exercise highlighting the reality of the issues that we're facing and the fact that by actually facing these facts, sitting with them, mourning somewhat for a loss of certain futures that we thought might be possible on the basis of not properly understanding this information, we can start to become comfortable with this information, incorporate it into our engineering practice, and move forward with engineered solutions that are fit for the future. And I'll hand over to Bridget to manage the discussion. Thank you for your time.
Thanks, Nathan. I'm still crossing my arms back and forth. That's super interesting. And there are a couple of questions, comments come through. So we'll rip into those. And if anybody has more, feel free to keep writing them in the Q&A with the Q&A button down the bottom there. I've got some as well, but I'll let the audience go first. So Nathan, you've talked a couple of times, mentioned nuclear, and that was in a couple of slides. What are your views on nuclear? And in particular, the question is, do you have any viewpoints on micro nuclear reactors, such as in submarines, for urban electricity supply or to power local centres? What's the summary story about that? I
think nuclear clearly has its place in the global energy mix. I mean, we have 440 roughly nuclear reactors, primarily in the global north, and part of the reason I live in New Zealand, because when we look at the reality of those reactors, we understand that there's very little in the way of long-term storage for the nuclear waste that's being generated by those reactors. that the spent fuel pools are full well beyond their design capacity and reliant on grid electricity to keep them running, that there are there is progress being made in terms of SMRs, small modular reactors, which is not to be dismissed out of hand. But I think the thing that I come back to with nuclear is probably a question around the rate at which it can be produced and relative to the rate at which this energy transition needs to progress to sustain the industrial systems which we rely on in the face of the resource depletion curves, which I've pointed to in this presentation. So I think that's where we're really, the conversation around nuclear, for example, nuclear in New Zealand, we know that at the moment our legislative environment forbids nuclear power, and that any nuclear solutions that might be applicable in the New Zealand market don't address the fossil fuel resource depletion challenge and would be probably 5-10 years away minimum from a consenting and change to legislation perspective.
So does that mean, like, legally and politically, we're not allowed to do them at the moment? And is there, I don't know much about nuclear and how it works, but is there a materials and essentially a fossil fuels requirement to get this stuff built, the infrastructure for nuclear as well?
Certainly large scale conventional nuclear reactors, the massive pulse of carbon required associated with all the concrete and so on, which absolutely is paid for itself over time if you don't account for the decommissioning costs, which is usually how these calculations are presented.
Right.
When you do include those, I think it presents a much poorer view of the overall carbon performance of nuclear, and doesn't address any of the other risks associated with long-term storage of fuel and decommissioning of plants in a scenario where we're already undergoing a level of, I'll say, deindustrialization because of the energy resource depletion situation that we find ourselves in.
So does that come back to that polycrisis slide where you had? I wonder if you could explain that maybe again in just ecological overshoot and what these things mean for engineers.
So I guess what I would say is that my own engineering training, I graduated from the University of Nottingham in 2000, did not include a systems view on energy systems. It did not include an understanding of ecology 101, and it did not include, therefore, understanding of things like planetary boundaries as they're known now. So some of that knowledge and understanding has come to us since I graduated. So it wasn't widely known. It was known, but it wasn't widely known at that time. But what I find is that when people talk about the technical potential for renewables to meet our energy requirements going forwards, then actually often what they're doing is ignoring the broader ecological implications. So you mentioned ecological overshoot there, Bridget, and I think that's a term which engineering as a profession needs to get much more familiar with. It relates, as I said, to those planetary boundaries, which is defined by the Stockholm Resilience Centre, and within that framework, we're shown to be at the latest iteration of that analysis in overshoots, that is exceeding the safe level of impact on the planetary system that they're looking at. And it's things like biogeochemical flows such as phosphorus and nitrogen, climate change, various other types of emissions. Those things are beyond the safe zone on, I think, 6 of the 9 boundaries that they've identified. So it's not just climate, although that is absolutely part of it, but it's that broader ecological impact of our industrial activities.
That's right. And it's not just keeping pandas alive, it's actually the life supporting capacity of the planet that we're talking about,
right? Right, exactly. Yeah. Ultimately, we're talking about a complex system which at some point reaches a tipping point, and when it goes over that tipping point, it goes to a new state where it's maybe less hospitable to the continuation of human society and life as we know it, and the ecosystem,
just those little things.
the natural world that we all hopefully know and love. Because I think
Gosh,
it's really
I would love
important.
to talk with you more about that, especially the tipping point, and whether you think there's likely to be a single or a crisis level tipping point, or whether there's just kind of a gradual political awakening where things happen. But I'll park that because this is not my show. So there's a question here about renewables. Are not renewables really only focused on electricity generation? What about all of the materials, built environment, etc., provided by oil? So what are the replacement resources? And I like this question because I had, I think it's probably from you, an awakening around that, in terms of it's not like everything that we, all the energy that we consume can be replaced by renewables, right? Some of it just isn't engineered that way.
That's right. Yeah. So substitutability of resources is the basic position in strategy and planning circles, and that comes from an economic framing of the energy transition that says that it's fundamentally blind to things like exergy. It's fundamentally blind to the net energy lens that I've been speaking to today, and as a result, it assumes that we can take the liquid fuel supply out of the total mix and replace it with electrification of everything and lots of renewable energy generation machinery, and just keep going with something like business as usual. And there's a whole variety of analyses which tend to contradict that. I'll just actually scroll through.
Oh, this is great. There's so many books. I recommend people look up the genre called cli-fi or climate fiction to get some authors' storytelling around what possible futures might lay out. I'm just in the middle of reading Kim Stanley Robinson, Ministry for the Future, which brings the science and politics and social science into some projections about how this might actually unfold in the next, like, short-term future, really, the next couple of decades.
Oops, we've gone past it. Sorry. Where are we?
These slides presumably all in the link you posted. So
they are in the link. That's
lots
right.
of
references. Lots of references there. Yeah. And sorry, for some reason I'm struggling to navigate through these. Let me see if I can do it this way. I come out of the presentation. But yeah, basically what I was going to point to was the analysis from the Geological Survey of Finland, which looks specifically at the material requirements of the energy transition and the way in which that has been, again, neglected in terms of this overall conversation.
That's Simon Michaud stuff.
Correct. Yeah. Here we go. That's it there. So the slide 43 and 44 there. Basically, what we're saying here is that there is a significant shortfall in critical raw materials. Now, Simon's scenarios were based on the EU's 2019 plan for net zero 2050, which basically is electrification of everything. And he kind of looked at that at the global scale and said, well, what would it actually require in mineral terms? It does have some criticisms which are valid, such as it didn't take into account developments in battery technology when it projected this lithium demand. But as I say, it was based on that 2019 net zero 2050 statement from the EU, and it was basically a rebuttal of that specific position. Things have changed in terms of battery technology. There are significant developments there. It doesn't, those developments don't address the fundamental requirement for things like copper. People say you can use aluminium to replace copper. They obviously haven't done a huge amount of looking at the specific electromechanical properties of copper and its replacement with aluminium when they're making those statements, because I don't believe that that is correct at all. And there's another slide here with a presentation linked from Mark Mills, which also talks about that mineral reality and the requirements for the mineral requirements for the energy transition, as it's currently envisaged.
Cool. So there's a question here about economic analysis. Do you have a view on how the economic analysis should have to change, or any examples on how it could change? Could it be as simple as using a social WACC, I'm not sure what that stands for, versus economic WACC?
WACC, so cost of capital, something cost of capital.
Maybe it's more like,
I'm guessing.
Like we talk about in transport, you know, financial and non-financial benefits, and basically stepping away from traditional economic analyses. Or appraisal.
So there are ways in which economic analysis can change. So Steve Keen has pointed to tweaks that could be made to the use of the Cobb-Douglas production function, which is the underlying of basis of a reasonable amount of neoclassical economic modeling and you know, the sort of, I guess you'd say, orthodox economics models that the likes of MB and so on rely on. What he points to is the exponentials for those various factors of production, labor and capital specifically, are too low, because the economists who set those in the analysis have assumed that the contribution of energy to the total economy is related to the percentage of energy, of total GDP, which is required to invest in the production of those energy resources. So it's something like 3 or 4%. And what he shows with his paper, which is available through one of the links in the presentation there, is that actually the requirement is to put that exponential much higher to show much higher relative contribution of energy to production, which is more in line with the understanding that energy is production, that if you don't have energy inputs to an economic system, then nothing happens. And as we saw in Europe in the last couple of years, as energy declines, you get some quite precipitous drops in GDP, which show the theoretical analysis. It's a guy called Tim Garrett from the US has described it. It's sometimes called the Garrett constant, which shows that the correlation between energy supply and economic output is correlated with an R squared of something in the region of 0.997, I think.
Yeah, and you've posted already a rebuttal to, you know, there's claims that we can decouple economic growth from carbon spend, but no evidence that that's possible at a global scale.
No, that's right.
It speaks to what you were saying about if New Zealand can do it and no one else will. When we're left with a dead planet, it's not in our interest either.
Well, it's not just the dead planet, right? It's actually that if the energy resource depletion situation is as I'm presenting it, and the total global economic system is reliant on growth in GDP to service the debt plus capital, the interest plus capital on the debt that's in the system, then actually understanding that leads us to the conclusion that a small drop in total global energy supply rate will start to contract economic activity at the global level. And actually, there's some evidence to suggest that that's what we're seeing now with this global slowdown, you know, and that actually we have a financial system which is reliant on that growth. And if we can't grow because of energy constraints, then it's going to look very different going forwards in terms of the projections of growth just can't be met. And
well, the whole way we organize ourselves as society.
Yeah, so what I've found when I've interrogated, say, the MB energy modeling work that's being done, which is the basis of a lot of the policy making in New Zealand around this, it's reliant on International Energy Agency economic projections. It looks primarily at supply, so GEM and SEDM and so on. The models that they use are classical sort of macroeconomic models, which don't take into account constraints on the rate of supply. sorry, it's based on demand prediction, not supply. It's based on demand projection. And so, you know, we look into the past, we see a rate of growth of 3.5% or whatever, project that into the future and assume that's where we're going. And therefore we must produce this much, we must import this much fuel. If we're going to electrify everything and substitute it, then we must build out this much renewables. And all of that is blind to the constraints, both material and energetic, that the resource depletion and the biophysical economics perspective brings.
We've had a few upvotes for this question. Can we go back to the Marsden Point slide? This is a question by Gregory Millen, and explore further why it was naive to close, and in the graphic where Marsden Point sits in the energy system global supply chain.
Yeah. Okay, so the statement that it was naive wasn't my statement. It was from this guy from the Australian Strategic Policy Centre. I think what he's pointing to, and the reason I've included that quote, is that ultimately we are headed into a period where the geopolitical wrangling that's associated with running short on energy and countries competing militarily for energy resource means that there may well, in fact, I would go as far as to say there probably will be disruptions to the smooth flow of energy which we've been reliant on over the past 30, 40 years. So we've not really had a situation in New Zealand. We've had a couple of instances in the last 6 months or so where, for example, a shipment or a consignment of aviation fuel has come into the country and it isn't to spec. And because it's not to spec and because we don't have Marsden Point, we can't blend it and get something that is the correct spec. So instead, what we're doing is sending it back, I assume, and asking them to do that elsewhere. And now that may be an Australian refinery, it might be back to Singapore. I don't actually understand enough about exactly how that system's working at the moment to know that. But I think that's a canary in the coal mine for us, really, in terms of our energy supply in New Zealand. We are at the end of some very long, very fragile supply chains as we're now getting all of our petrol and diesel as refined product primarily from Singaporean refineries. And there are lots of people closer to that refinery infrastructure who have military capacity to compete for that resource. New Zealand doesn't have that capacity. We rely on our strategic partners for that sort of, stick, if you like, and we can, dangle the carrot of better payments, and we have, in terms of our strategic petroleum reserve, only maybe I think it was something like a third of the 90 days, which is the global sort of standard for strategic petroleum reserves, actually as refined fuel in tanks on the ground in country. The rest of it is preferential buy options. It's agreements, bilateral agreements with the likes of Australia, because I think some of it is stored in tanks over there. All of that assumes that it can get here. It assumes that the global economic system is functioning again. And in that context, it's naive to shut down a refinery or to allow refining New Zealand to shut down Marsden Point, because yes, it wasn't set up to produce to refine New Zealand crude. Yes, it would have taken a significant investment to make it so that it could refine enough to provide a significant percentage. But even as it was in its structure at the point at which it was closed down, my understanding is that it could have taken some of the condensate, which is the lighter stuff that we produce in the Maui fields and so on, and that we could have actually used that oil to produce a small percentage of our average annual demand, which could be used to keep essential services running, to keep the emergency services and so on supplied. It's certainly nothing like enough to keep business as usual or anything like it, but it could have been a strategic asset had we chosen to invest in retaining the staff and the skills and nationalising that asset.
So do you think there's a bit of a perhaps immature or basic view from some of the public that it's an all or nothing kind of, you know, Extinction Rebellion, no more fossil fuels? It's not actually that simple, especially in the short term, because you could actually increase emissions with some of these decisions.
This is a challenge for engineers when we're answering this sort of question, right? Because, you know, we know that the zeitgeist is against fossil fuel and the continuation of fossil fuel use, and rightly so from an ecological and ecosystems perspective. But we also know pragmatically as engineers that we want solutions that work. And we know that actually, you know, the idea that we can transition rapidly to renewable
in an
energy,
instant, isn't it? Yeah, that's right.
well, I mean, in a virtual instant, you know, even over 10, 15 years in terms of actual energy transition strategies is an instant.
That's such a short time frame, exactly. Yeah.
And you know, we really don't have capacity to do this in the way that it's being talked about commonly in the public. As much as we'd like to think we do, you know, people will point to, well, the cost of renewables is continuing to decline, and that argument actually doesn't take into account the last 2 or 3 years worth of data where, you know, the price of lithium did a moonshot. It spiked by something like 900% about 18 months, 2 years ago, and it's come back down a bit since then. And you know, it's kind of up and down, it's volatile, but it is trading well above the historic average. And you know, inputs to renewable energy systems in terms of material inputs are something like 80% of the marginal cost of production. And so, you know, that's a significant proportion of the cost of those renewables, which is inflexible and which is based on the price of the raw materials, the refined materials. As that price continues to increase, the price of renewables will go back up. And as everybody globally gets on the same train and
wants all the electric cars all straight away, yeah,
as we're doing, you know, those prices will continue to go up. You know, that is basic supply and demand. You know, it's something that economics does have right. You know, as the demand for that product increases, the price is going to spike. And I just don't understand why people, you know, ignore that reality.
Well, maybe we need a whole other webinar on capitalism and markets. And so there's a question here, kind of, well, my brain goes there anyway. Is fusion energy a panacea? Will it come quickly enough? Will it be shared widely enough to make a difference? Or a related question from my brain is that if we did have a sudden golden energy zorb that could do anything we wanted, would that be a good thing for humanity and the rest of,
Yeah, so fusion energy is not a panacea. There's a number of parts of this story. The basic quote that you often hear, and I think this is probably the simplest way to put it, is that fusion energy is 20 years away and always will be.
Like autonomous cars.
You're trying to create a mini sun inside a magnetic field and sustain that reaction over time, and then bleed off some of the surplus energy that theoretically can be generated. We haven't really got to the point globally with the 40 odd years of trying and the trillions of dollars that have been invested, where we can get a significantly positive net return from fusion reactions. The small bits of positive news where, you know, the reactor did provide a positive energy supply for the 5 minutes it was running, failed to say that that's a several $billion-dollar machine, which by the end of that several minutes was wrecked because of the temperatures involved. Wow. And will need to be significantly rebuilt. I mean, it's just, it really is nowhere near being a useful power source at this point. And to your broader question, I always refer people back to, there's a really nice post by a physicist from the US called Tom Murphy, who wrote a post called Galactic Scale Energy, and I believe that might be in my slides somewhere, but look up Galactic Scale Energy, Tom Murphy, on the Do the Math blog. And he talks about the fact that if we were to produce some, you know, 0 point energy power source or something of that nature and continue with economic growth, business as usual, 2-3% growth, then somewhere around the 300-year mark, we hit the surface of the Earth being the same temperature as boiling water. And that's not anything to do with climate effects. That's just purely the total quantum of energy that we'd be using at that point, and the low-grade heat that's dissipated through the inefficiencies inherent in physical processes that we understand as engineers.
Oh, I think we've got just time for one last question, and it's kind of bringing back to that ethics and, that the planet is a global system. From Stephen Bright, he says, it looks like 1950s levels of energy consumption could be a sweet spot. However, I assume those levels were heavily first world biased. What would be the global consumption look like if everyone was kept at that level? Or is there conversation around what a sustainable level of consumption with today's population might be?
Yeah, it's a really good question. Funnily enough, somebody asked me this question a couple of days ago, and I went looking back through my notes, and I don't know of any analysis that specifically addressed that question, actually. So that specifically said, okay, what could be sustained realistically, with a net energy lens, with a resource depletion understanding, with the sort of global polycrisis going on in the background. It will be a very interesting piece of analysis to do, and it's something that I think we probably should be doing globally. My guess, and my guess is based on the requirements of the trends in terms of energy resource depletion, is that if we project out to say 2050, purely on the basis of energy resource depletion, we'll be operating globally with an energy budget of something that's probably around about 10 to 20% of our current energy throughput in the economy, and that might be sustainable at something like that level. So, for first world countries like New Zealand, this is a really challenging topic because, we have such high energy metabolisms in our economic systems that actually recognizing that for us, it's going to be something like an 80-90% drop in total energy throughput by 2050 on the basis of this biophysical understanding, really, leads people to feel like that slide with the cat on it,
Yeah, the phrase paradigm shift doesn't really cut it, does it?
It doesn't, and that's one of the biggest challenges I think we face as engineers, is if we go to clients with this understanding and we say, actually, probably, your business doesn't have a long-term future, because,
or governments for that matter,
or governments, we're primed psychologically to look for good news. The good news in this context, and let's finish on this point, is that actually, when you go to these third world countries and, collapsing living standards to, say, the same conditions as the people who grow our coffee is what we're talking about here. I hear two things from Kiwis when they come back from those countries. They say to me consistently, they're the poorest people I've ever met, and they're the happiest people.
Yeah, the happiest. The great simplification, right?
Absolutely, and Nate Hagen's work is well worth name checking at this point. I've got that in my.
Yeah, I saw a link there. I recommend that too.
There's a whole load of slides there with further presentations on this subject. If there's one book that you're going to read, Surviving the Future: Culture, Carnival and Capital in the Aftermath of the Market Economy, is highly recommended, and that is a readable summary of a larger work called Lean Logic, which is freely available as a dictionary of environmental manners, and
wonderful.
through that link there. So yeah, thank you very much for your time.
Thanks so much, Nathan. That's been brilliant. I feel like we could schedule another dozen webinars off the back of this, and I'm sure Engineering New Zealand will be interested in fleshing out its program to just keep talking about the real issues and raising awareness amongst engineers. So thanks very much to everybody for attending, and I'll just hand back to Bryony to close.
Thank you.
Yes, just second what Bridget was saying. That was really interesting, and I think has got a lot of people thinking, and definitely me at all levels of where you are with this, and no easy problems to solve, but you know, we're as engineers, we're here to take on these challenges. So I thank you so much for your time. You've got so many ideas, and your research in this area is just so impressive. So thank you, and thank you, Bridget, for your time as well. I know we've both all got to everyone on here, and everyone's got to dash. Ka kite, and yeah, again, thank you so much.
Ka kite.
Okay, bye bye.